All right, so welcome. We're going to talk about the DragGAN paper today. Let me share my screen. And we will start out with the video, and then if after he does the brief explanation, we want to see more demos, we can pause. We look at some more demos before we go on to the technical explanation of how it all works. And that's the plan for today.
Okay. In this video, we will have a look at the DragGAN paper that allows us to easily edit images via drag and drop. While some people have already called this the end of Photoshop, I certainly don't believe that because there's still some limitations to this approach. However, we will have a look at all of it. We will have a look at the paper, re-implement the paper in PyTorch, edit our own images, and in between, I will also unveil some limitations of this approach. So today, we will gain a deep understanding about the DragGAN paper. Hi and welcome back, guys. I know it has been a long time since my last video. Sincere apologies for that. I even got asked if everything is okay with me. Yes, please don't worry, I'm fine. I just have been very busy the last 2 months, as life sometimes is. And yeah, I even got this comment from Jimmy, who asked if everything is fine and he misses my content, which I really appreciate. Thank you so much. All your comments always motivate me to keep going, to create new videos, so please keep them coming. I always appreciate them. Unfortunately, it's hard for me to reply to all of them, but I feel like I can quite confidently say I've read all your comments so far. So please never hesitate to give me your feedback, ideas, anything, how you like the video. I am always happy to hear your feedback about my videos. And yeah, also all your nice words, they really mean a lot to me. So thank you for that. And now let's head back to the DragGAN paper. And honestly, I didn't have much experience with GANs before reading the DragGAN paper, because I felt like the last 1.5 years, the majority of people have focused on diffusion models, which are superior and generating high quality images. But as we can see with this work, GANs can also have advantages when it comes to image editing and having a better control over the image editing process. And because of this, besides reading the DragGAN paper, I also read some other papers to really gain some fundamental knowledge about GANs. And once I had collected all the needed knowledge, it was super easy for me to understand the DragGAN paper. While the first time I read it, I had some issues and couldn't follow all of it. And because of this, I decided to also give you a brief history about GANs. And with this brief history, you will be able to easily understand the DragGAN paper. Okay, should we start? Let's go. Okay, let's first recap how a generative adversarial network actually looks like. And here we can see an example of it, while we have here our generator, the generative part, and our discriminator, the discriminative part. And we can imagine this as our generator takes a low-dimensional input vector and maps it to a high-dimensional realistic output image, which could look like this one. And our discriminator then decides if this is a realistic image or not. So our discriminator basically sees the images generated by our generator and then has to decide if this image by the generator is a real one or not. And this is basically a little bit like a game between the two of them. That's also why it's called adversarial, because they're playing against each other, and the training is in a way alternating. So first we freeze the weights of our generator so that only the discriminator gets updated, and then once we have trained our discriminator a little bit better, then we freeze the weights of the discriminator, and then our generator gets optimized and it gets basically better at generating images. And another way we can think of the discriminator is basically as the perfect loss function, because it's very hard for us humans to describe in a mathematical function how a realistic image should look like, especially in a mathematical function that is easy computable and differentiable. So basically, since this is like kind of like a complex task, we just leave it to the discriminator to learn this perfect loss function. And then using this perfect loss function, our generator learns how to generate highly realistic output images. And another property that we can see here, our generator gets a low-dimensional input vector and maps this input vector to an output image. Yeah, and you might be thinking, why is he talking so much about this low-dimensional input vector? This will become very important for the DragGAN paper. And what we can basically imagine, as I said, the generator is a mapping function in a way from a low-dimensional input vector to a high-dimensional output image. And another way to think of this is to look at this paper that we can see here, which is basically a 2D subspace, and by bending and folding it, we can basically transform it into a way different representation or shape, as you can see here, right? And now let's imagine this will be our space of all possible output images. And in there are a lot of noisy images that don't look realistic at all. Maybe you can refer this as if your TV has a broken connection. Maybe at least my older audience can refer to this. And now imagine this will be a realistic output image, this will be one, this will be one. So what we're basically learning here is called an image manifold. We're trying to bend and transform a lower dimensional input space so that we can map our inputs only to realistic output images. So the generator basically learns this image manifold during training. And another property that often occurs is that neighboring input vectors that are also called latents correspond to images that are visually similar in the output basically. And by manipulating certain elements in the input vector, we can then basically add it in our output images, something like the pose, the hairstyle, if the eyes are open or closed, which is a very important property for the DragGAN paper, which you will see later why. And one model which is exploiting this even further is the StyleGAN or StyleGAN 2 model. And the whole assumption of this model is that we can basically reconstruct an output image just by applying a certain set or amount of styles to the image. What does that exactly mean? So as you could have seen here, we're taking our input vector and mapping it to a way higher dimensional space, right? And the problem here is that those output images are directly related to our input vector. So let's say in our training data or in our training data distribution, we had a lot of images with men and short hairs, while we only have a few men with long hairs. And the problem with this is that the model will be way better at generating images with men and short hair than men with long hair. But ideally, our model should also be able to generate men with long hair in a good style or in a good way. And to overcome this, the StyleGAN model introduced something which is an intermediate representation. So instead of directly working in our input vector, we have a mapping network in between that maps our input vector to an intermediate latent space, which is actually a vector of the same dimension as the input vector, but it just takes away the direct dependency of our input vector to the output image. And I found the reason for this approach very well explained in another Medium article, which I just quote here. The goal is to encode the input vector into an intermediate vector whose different elements control different visual features. This is a non-trivial process since the ability to control visual features with the input vector is limited, as it must follow the probability density of the training data, for example, the man with short or long hair. For example, if images of people with black hair are common in the dataset, then more input values will be mapped to that feature. As a result, the model isn't capable of mapping parts of the input, elements in the vector, to features. Features could be, for example, pose, hairstyle, eyes opened or closed, a phenomenon called feature entanglement. However, by using another neural network, the model can generate a vector that doesn't have to follow the training data distribution and can reduce the correlation between features. So in a way, in our intermediate representation, we can better cover features that are not as often represented in our training data distribution. So we make them less correlated or less dependent on the training data distribution. And now let's have a look again at the StyleGAN architecture. So first we map our input vector to an intermediate representation, which is called W, and then by affine transformations, which could be, for example, a fully connected layer, we then map those to different styles and apply them within the individual blocks of our network. So for example, one block is the 4x4 dimension, then the 8x8, and if we generate a 1024 times 1024 image, we would have here 7 more blocks. So in total, our network would have 9 of those blocks, while we apply 2 styles per block. So what?
All right, so I think he did a decent job just covering the basics of the GAN. You have a generator, which is trying to generate realistic images, and you train it on some data set. So if you train it on celebrity faces, then it's going to generate faces. If you train it on different animals, then it'll generate those different animals. And the discriminator's job is just, it'll get presented half generated images, half actual images from your training set. And so some of them are real and some of them are fake, and it's supposed to try and figure out which one's real and fake. So if the generator does a really good job, then the poor discriminator is just going to be flipping the coin. It has no idea which one's real, which one's fake. The style GAN, I think actually we talked about this, but it was before we started recording videos to YouTube. And so the main thing is this latent that you start with here, you actually, like in Python, run a random number generator. So if this is a latent length 128, you generate 128, random numbers between 0 and 1 or something like that. So you send it through this fully connected neural network. It's got enough layers that it's very nonlinear, okay? And it transforms it into another, it's still just a vector of 128 floats, but obviously they're now different from your original. So in the DragGAN paper, we're going to be talking about this W a lot, if I recall. The rest of the style GAN you don't really need to know that much about, except that in this particular diagram, the data flows from top to bottom. A lot of diagrams are the other direction. They go bottom up, okay? And what will happen is this thing will generate more coarse features. So let's say you're just doing celebrity faces, okay? So it's going to maybe do like the general pose. Are they looking directly at the camera? Are they looking to the side? Maybe long hair, short hair, skin tone, hair color. That'll be some of like the early stuff. And then maybe in the middle layer, you get other features like eye size, eye color, shape of nose. And then in the finer levels, you get things like the precise length of the hair. Maybe you get earrings, whether they've got like a mole, a beauty spot, color of lipstick, tiny things. And so it goes from coarse to fine features, and not all the layers are shown here. This is just a snippet from the middle of this very tall stack as it goes from coarse to fine.
Hey,
So,
Ken.
yeah.
I wonder if you could scroll back just a little bit. That quote that he had out of the Medium article. It was the first time I'd seen that description of the purpose of the fully connected network, I think, or mapping network, I guess they call it.
Yeah. So when you randomly generate 128 floats, they're all going to uniformly be between 0 and 1.
Right.
Okay. But let's just say it's not necessarily going to be this simple, but let's just say the 17th floating point number is eye color. Well, eye color should not be uniform necessarily between brown and blue or whatever. Like maybe it's 50% brown and only 15% blue, right? Or maybe if one of them is earrings, you want to say a lot more women are going to have earrings and a lot fewer men are going to have earrings, or a lot fewer men are going to have long dangly earrings or whatever. So this comment is sort of talking about the fact that the Z's are going to be uniform between 0 and 1 for all 128 dimensions, but the W's can have all sorts of funky distributions in order to match what you want as opposed to uniform.
So what the sentence I'm picking up on is that last one. So this feature called feature entanglement. It says, however, by using another neural network, the model can generate vector, doesn't have to follow the training data distribution, and can reduce the correlation between features. I just wondered if anybody had intuition as to what would enable that or drive that. I can understand what the sentence says. I just can't understand anything that would cause the mapping network to do that.
So in this architecture, if we let the video go forward a little, scroll down. This W goes through a single matrix multiply, okay, and he calls it affine because it's got a bias, so it's not just a multiply; it's a multiply and plus a bias or whatever. But for now, let's just ignore this and assume that you did an identity matrix there. So W just goes straight in as is. Okay. So if you wanted women to have earrings 90% of the time and men to have earrings 10% of the time. With your Z's, it's going to be kind of weird because that would mean that like 0.1 through 1.0 would all have to represent with earring, and just 0 to 0.1 would represent without. But that's only true for women, and then for men, you want it to be 0 to 0.9 means no earring, right? So what is the model supposed to do with that number to tell it what to do? However, you could easily have a layer of neural networks that says float number 45 says male or female, and float number 17, if it's a female, I will map 0.5 through 1 to the range 1 to 0.1 to 1. But for men, I will map 0 to 0.9 to 0 and only 0.9 to 1 to 1, right? It can do all of those kinds of complex relationships. So then, even though you're starting with a uniform distribution, you can get your W's to be distributed exactly the way you want, and the correlations between the different numbers in the W can be whichever way you want.
Okay. I can see that mapping, how it gets out of training data distribution. I don't quite understand, but I don't want to run us down a rat hole. So yeah.
Okay, yeah. So the bottom line is that your W's are going to be unevenly distributed. And this, if you think about this network in reverse, what it's doing is it's taking the uneven W's and allowing you to use a perfectly uniform random number generator to get W's that are not uniform.
Yep.
So it's really I think it kind of makes more sense in reverse, but you are running it in the forward direction.
I like that. That helped me understand it a lot, Ted, actually. Sorry to interject here, just because I was thinking the same thing that Roger was, as he was saying. It's like, how do you do that? Like, how can a forward pass mapping network be aware of features? So he described what features were, but he didn't describe how you do that. And thinking about it in reverse, which is again, obviously the backdrop kind of part of it, the difference between uniformity and the actual distribution is in its essence the features, right? I mean, I think that's kind of the nature of it.
Yep.
And so if you were, it's basically like a diffusion network backwards. What you just described is essentially a diffusion network backwards.
I don't know if it's exactly that, but yes, it is definitely figuring out how to map this uniform distribution to the features you want. And I've been talking about them as if they're going to be super simplistically in your basis. And that's ultimately what the authors of StyleGAN wanted. Okay, they wanted to be able to just slide float number 17 up and down and have that change the length of the hair and nothing else. And they wanted to be able to slide, float number 3 and have it change the eye color and nothing else, not the shape.
Yeah, I mean, the way that I think of, again, let me go back to actually, the more I said that, think about what I said about the diffusion model, the more I kind of like that, because essentially what a diffusion model does is it takes uniformity that isn't meaningful and makes it meaningful. And what we're trying to do is take a distribution that is not uniform but is meaningful and map it into uniformity. And yeah, I the more I think about it, the more that analogy holds.
Okay, good.
And it's kind of the same process, that Roger, if that makes sense, that essentially you're taking a mapping which is uneven but contains the semantic meaning of your data distribution, extracting the features from it into that network. But again, as Ted said, in reverse, but because it's fully connected, it doesn't matter which direction you're going. And to produce a sampling methodology that more closely reflects uniformity.
Yeah, and so the left-hand side is mapping the features you care about: eye color, whether they're smiling or not, hair color, hairstyle, hair length, all of those things. It's doing that. And then the right-hand side, which we haven't really talked about so much, is what takes that concept, curly versus straight hair, and turns it into pixels.
Thumbs up or thumbs down, Roger?
Oh, I'm good. I'm good.
All right, cool. Yeah, and I like that he went over that, because I certainly have seen the architecture, but never really thought about exactly what the ZW process is. But I think Dave kind of nailed it. All right, so we'll keep going. I can't remember if he talks a little bit more about StyleGAN, but I just wanted to kind of give that grounding and just sort of sneak preview. He's going to say it really quickly, but ultimately what the authors said is they did some experiments and they found that if they try and fiddle with things at the coarse level, it's too coarse. And if they fiddle things at the super fine level, they can't change the image enough. Because once you get to the very end of it, all you can do is just slightly change whether the person has like perfect skin or slightly not, or whether the hair is, you know, a little shiny or not, right? So they ultimately did something like they picked layer 6 and they said that's the place where all of the work of DragGAN is going to modify things.
Which is called W, and then by affine transformations, which could be, for example, a fully connected layer, we then map those to different styles and apply them within the individual blocks of our network. So, for example, one block is the 4x4 dimension, then the 8x8, and if we generate a 1024 times 1024 image, we would have here 7 more blocks. So in total, our network would have 9 of those blocks, while we apply 2 styles per block. So what those affine transformations basically do is, in our intermediate input vector, which is basically an abstraction of our different styles, we then learn a transformation that allows us to apply certain styles at a different blocks level. So the impact of those different styles on the generation of our output vector has also different effects depending on the scale. So by scale, I mean if it's like 4x4 or 8x8 or in the higher resolution blocks already. So the authors distinguish the effect of the styles in 3 different categories. So we can see here coarse, which is 4x4 to 8x8, where we have high-level aspects such as pose, general hairstyle, face shape, and eyeglasses, while we have middle from 16x16 to 32x32, and here we have smaller scale facial features, hairstyle, eyes open and close. So this will be a finer hairstyle, eyes open or closed. And then in the upper higher resolution generator blocks, the styles only have an impact on color scheme and microstructure, which are very subtle. And since this was all pretty dry, and the authors created a really great visualization to better understand the impact of those different styles, I would say let's have a look at them to better understand what this actually means, like how the different styles on the individual scales have an impact on the generating process. And before we do so, there's one thing that I would really like to point out, and this is that the styles can be manipulated individually, allowing us to change attributes like age, gender, pose, and expression, which is basically the foundation for the DragGAN paper, which I will show you after this. And now on the left hand side we can see the styles. So we see the individual pictures, and out of those pictures we basically take the styles of those pictures and apply them to the picture on the right hand side, the bigger picture. And as discussed before, we have 3 different categories of styles. So we have the coarse, middle, and fine styles. And now we can see that the coarse styles impact high-level aspects like the pose of the person, the facial shape, or the hairstyle, while the middle styles are more impacting smaller scale facial features, especially if we're paying attention to the eyes in this example, or also to the hairstyle. And now for the fine styles, we can see that the fine styles only have impact on the color scheme and the microstructure of the image. Okay, and after this brief or not so brief introduction to GANs, we now can finally have a look at the DragGAN paper, which you can see here. And yeah, why was this introduction so long about the GANs? This paper is really, or the whole DragGAN paper really relies on the StyleGAN model or generator. As I also describe here, our study is based on the StyleGAN 2 architecture, and it's really important to have an understanding for the StyleGAN 2 generator to really understand what's going on in this paper and why this approach works. That's why I spent so much time with you going through all this, because I also first read this paper and then read the DragGAN paper, and I wouldn't recommend to do it this way. So, you know, in this video I already gave you, in my opinion, the best structure to understand this paper. And to be honest, in this paper there are actually two major contributions or two major techniques that help us to really edit images just via drag and drop. So we select our handle points, multiple in our picture, and select where we would like them to move. And then the whole thing is just an optimization technique. So we don't even need to fine tune or train a new GAN or I don't know, any kind of model. We really just optimize our intermediate latent vector W, which you saw earlier in the DragGAN architecture, but more on that later. So what are those two major techniques that this paper proposes? The first one is the motion supervision, and the second one is a point tracking. But let's start with the motion supervision. And the key idea here is that the intermediate features of the generator of this DragGAN 2 architecture are very discriminative, such that a simple loss suffices to supervise the motion. So what this motion supervision proposes is that we can take the feature maps after the sixth layer or sixth block of this DragGAN 2 architecture, which we saw here. So this is basically the first, the second in our network. So we have a resolution of, I think it should be 256 times 256. And based on those feature maps, which according to the authors have performed the best among all features due to a good trade-off between resolution and discriminativeness. And then we resize those feature maps, which have a resolution of 256, to have the same resolution as the final image. And this depends, the DragGAN has different versions, but let's say if we're interested in the human faces that we also saw before in that video, then it will be an output resolution of 1024 pixels. So we would use bilinear interpolation to just upsample the feature maps after the sixth block to this size. And what we would then do is select our handle points, which we could see here in this picture as a red handle point, and we have our target point, this one. Here we only have one, but technically we can, I don't know, I think there's no upper limit, so you can use as many as you want. The idea then is to calculate a normalized direction vector, which is this one. So what does this exactly mean? TI is basically our target point, and then we have PI, which is our handle point, and with this we just calculate a normalized vector that is pointing from our handle point to our target point. So this way we'll use this direction vector here to basically move our handle point towards our target. And how can we do that? First we need to figure out what this QI is, and for this we can see that QI are all elements or pixels inside this omega-1, and we pass our handle point I and at a distance R1. And I felt like this is described a little bit more complicated than it actually needs to be in a way. So in practice R1 is just set to 3, so we just take all neighboring pixels with a distance less than 3, and to just make it easier to understand, I made this very easy sketch here. So you can see this is our handle point, and in omega-1 are all those pixels that have a distance less than 3. So we can see here the distance is 2, here's 2. I think this should also be in, so it's not circular. So we also consider those. So we just have an image patch. So we can think of omega-1 as just an image patch, and all QIs are in this image patch. So elements in this. So just like neighboring pixels, which makes this way easier to understand. And we remember our feature maps after the sixth block of the DragGAN generator. And I mean, not only have one feature map, but we have actually 128 in a row. So imagine we have a book of 126 pages, and we would chop off a small piece, like basically at 1 pixel. Then we have, like in depth, basically 1 vector. So this is a vector, and this is also a vector. But since our direction vector that is pointing from our handle point to our target point is normalized, we don't have an integer here, which doesn't allow us to access or index our feature maps, because we basically need integer pixels to index the feature maps. So what we're doing here, we need bilinear interpolation. And then for both of them, we calculate the L1 distance, which is just to measure how far those two are away from each other. And this we then do for all different handle points. So we can see this is like a summation for one handle point, and here we iterate over n, the number of handle points we have. So our loss just calculates for each handle point. We just take the handle point right now. We basically calculate a version that is slightly moved towards our target point, which could be, for example, here. And we calculate the difference between the two of them, and this is our loss. And one term that we haven't talked about in this loss function is the second term, this.
All right. So it's funny, the first time I listened to it, I thought it made more sense. And then like just listening to him now, I was like, oh, this is actually, for me, it was still a little bit confusing. So I believe that what he's saying is if you look at so first thing you do is you run style GAN, okay, and it outputs a picture of a lion, and you say that's my starting point picture. That's the one I like this lion, but whatever they said, I want to move the nose, to the right. Okay, I want the lion to be looking, that way instead of directly at the camera. All right. So then I believe what it does is they just take a little patch around where your red dot is that you picked. Okay, and let's say the direction you picked was exactly to the right. It's not on an angle or anything. It's just completely to the right. In that case, then I think what they would do is they would just say, okay, let's move it one to the right, this small patch. All right. And now what I'm going to do is I'm basically going to take all the possible like W vectors that are really close to our actual W. They're just off by a little bit in each direction. And I'm going to see which one generates the closest resulting picture to me shifting this one pixel to the right. And it's quite possible that none of them will be exactly spot on. They might all be a little bit off, but whichever one is the best, that's the one I'm going to use as the starting point for step 2. And I'm going to repeat this process. I'm going to do it over and over and over again. And so what they're taking advantage of the fact is that if making a teeny tiny tweak to your inputs to the GAN caused a dramatic change. If you did this one teeny tweak and it changed it from a lion to an elephant, then you'd be screwed. This process would not work. Okay. Instead, what you want is you want a process where if you just move it a teeny little bit, then a small change in sort of the random number that you start the random numbers that you start with can get you very close to that teeny tiny change that you want. The issue is you don't know which change to make. And so when I first heard about this paper, I thought, how on earth did you reverse engineer which change to make? And what we're going to see is that they're not actually going to reverse engineer it. They're just going to exhaustively search all the nearby points, so to speak. And they'll use a little bit of gradient descent, but they're basically.
So is this essentially like a brute force computation of a manifold, right? Like you use the term manifold,
yeah,
the image space manifold. Like what you just described is essentially computing the gradients,
yeah,
again, brute force mechanically, right? Versus
yeah,
differentiably.
And I think there's one place where they use a min and there's another place where they actually use gradient descent. So I'm going to have to let the video play for the exact details. But just to kind of give you the big picture, okay, we're just going to try to first thing we're doing is we're sort of like building a target to say like move things one pixel to the right. And then we're going to say what tweak to our random numbers gets us closest in that direction. And then let's move it a little bit more and a little bit more and a little bit more. And so, yeah, I don't remember the details, but it is definitely not the case like when you say, the inverse of the x squared function is the square root function. It is not that, okay? It is more of an exhaustive kind of thing. I don't know if it's completely brute force, but it's yeah, there's no closed form anything.
Can we say
And this
that?
is all at a, what you're saying the term, using the term pixel, but this is all at a mid-layer feature map, right?
Yeah, and in order to just make the math really simple, instead of using a feature map that's different resolution, they blew it up so that it's the exact same resolution as your original image. And so that way, when you talk about moving 1 pixel in the image, it really is moving 1 pixel in the feature map.
Oh, okay.
Yeah, Shulin, you have your hand raised?
Yeah, so I'm thinking of that, like, could it be kind of like a combination of two? So the first one is detecting is try to make sure that the other points have the closest to the points that you want to move to. And the second one is kind of like you want to, while you want the other points to move to the desired position, you also want it to kind of like remain, you also want the shape to be remained. So you don't want to kind of like all the points just like being twisted in one point. You still want to kind of like maintain the relative distance between those two so that your graph doesn't deform too much. And you have a lambda to kind of like adjust the thing. So is that this loss function is about?
So, yeah, so he's about to explain the second term, okay, which really only applies when you use a mask. Okay, so when you mask and you say this is the only part I want to move, then you're penalized if anything outside of the masked region changes. Okay, what we're really counting on here is that the GAN has built in, like let's say you're doing faces, okay, the GAN has built in real world understanding of how faces work. Okay, and so if you say move the nose an inch in one side, the whole head has to go with it. You can't just move the nose so that it's no longer in the middle of the face. Okay,
Yeah.
it has a lot of that understanding. At the very end of the video, he shows that if you try and do something too much, like you try and move the nose all the way over here, then it'll actually get lost and confused and you just get this distorted mess and it doesn't look like a face anymore. Okay.
Or if we see the pictures, so I see sort of kind of like the experiment of it is basically kind of like you have one image that is kind of like taking in the front and you want to turn the head left or right. But when you turn it the left or so if we see kind of like taking pictures as a projection, so when you turn left or right, you're kind of like, you may have like, when you turn left, you may have your right face show up more and your left face show up less. But this is kind of like, but the relative position of your nose to your eyes is going to be the same. So I'm just thinking that maybe that's what the M is about. So it's still kind of like.
No, that's not the M. The GAN just has real world knowledge and takes care of all that for you.
Okay.
So in the one they show where they have a picture of a lion just sitting there staring at you doing nothing, okay, and they take the top lip and the bottom lip and they have the top lip move up and the bottom lip move down. When the lion opens its mouth, it has teeth because the GAN just knows that lion has teeth. It's not going to draw a big black empty circle once the mouth opens.
It's like a knowledge-based matrix that tell you.
So as long as you stay like close enough to its training set and the real world knowledge it has, you're okay. But if you do something right, so like if you took someone with closed eyes and you wanted to open the eyes, okay, that would be fine. But if you wanted to kind of move the eyelid like all the way up here, it's guaranteed to fail because it has no idea how to have an eyelid move that far. Does that make sense?
Got it. Thank you.
Yeah. But Shulin, I think Ted had said that the second term is going to be described as that's the loss function for the masking. So you'll see later where you can say, don't change things out here, only change things in a certain area.
Got it. Thank you.
Okay. Yeah. So basically what we're going to try to do is we're going to take the image, we're going to move it in the feature map, we're going to move it in the direction you want. And if you have a mask, then we're going to like try and not move any of that. So, all right. Let it play because he's probably going to explain some of the other parts better and actually reference the paper.
This one here, I found this equation a little bit hard to read because both some symbols are just denoted for this expression. So we basically could put parentheses around those two here because, or just replace this one before both some symbols, because this term is just for our mask. So what we're seeing here, the F0 are our initial feature maps of the initial image, and these are the feature maps of the updated latent code. So during our optimization, those feature maps here will get updated while those remain the same the whole time. So what we are basically calculating here, similar to what we're doing here, we're just calculating the distance. How much have those feature maps changed during our optimization? And we multiply this with our mask, which is a binary mask. So for example, we would just highlight a certain area. For example, that could be the face. And all the values in our mask where the face is would be 1. So basically this expression would be a 0. And then the whole distance will be 0 because we multiply it by 0. And what is the impact or the effect of this? So within our mask, we don't want to penalize the loss for any changes in the feature maps, while outside the mask, this is actually the whole reason why we introduced the mask, we don't want any changes. What this term actually says is basically the background without the mask should remain the same and shouldn't be changed at all. So only pixels inside the mask should be updated and changed. And this is just a scaling parameter, or how much we want to penalize the generator for changing pixels in the background or the feature maps in the background. And then we use this loss and basically propagate the loss back into our model inside the generator, while all the weights of our generator are frozen. So the only thing that can be updated is our intermediate latent code W. So this is basically the whole assumption of this. This is also why I in the start said like, oh, imagine like an image manifold. We have a low dimensional input vector and then have a high resolution output image. And this is basically just a mapping. So what we're doing, we're propagating through our mapping all the errors or the loss that we have calculated here to optimize our low dimensional input vector or our low dimensional intermediate latent that we have in our StyleGAN architecture. We can just use a loss function, propagate it back, and this way we optimize our intermediate latent and are able to change the pose of a person. And we're not doing this at once. Basically, we only do the motion supervision once, but we do multiple steps. And one thing that maybe now you could think of is, okay, we have updated our intermediate latent code. So for example, we're taking me right now. Here's our handle point, so it's my nose, and we want my nose to move to this direction. So what I would do then is, like, after one motion supervision, maybe I look a little bit like this, but eventually I would look like this, right? So my nose is a little bit shifting, while we can see here our PI is technically not updated, right? It remains at the same place, but to guarantee that our small steps work and our small updates are done at the right direction. For example, let's imagine I move my nose and our handle point remains here. So at some point, those updates will be wrong, right? Because we would start updating, for example, my cheek here instead of my nose. And because of this, we need the point tracking, which allows us to track our selected handle points in a way. And one more time, there are approaches that are very complex and, for example, need neural networks to track those points. And once again, this paper does solely rely on the discriminativeness of the intermediate feature maps of the StyleGAN architecture, which is very, the whole paper, I really like it. It's different. It's not like we're training a model or something. It's just very clever, very smart. But if you know the StyleGAN architecture, it's also very easy to understand. Yes, and this time we need to keep in mind for the point tracking, the motion supervision for this iteration has already taken place. So we're working with an updated or new latent code, new feature maps, and also new image, because they are all already slightly moved towards our target point. So I'll stick to my face basically being moved to this direction. And what we're doing then, first we need to kind of store our initial handle point or the feature maps of our initial handle point. So F0 here are the feature maps after the 6th layer of the StyleGAN 2 generator of our initial image. So for example, where my face is right now, centered. So and now we would take the feature map right from my nose here, and we will always use them like we can see here, the F1, to compare. So even if my face is somewhere here or here, we would still compare with this initial feature map or feature vector of my nose, to find my nose again at this point here. So you know, we're trying to find this initial handle point that we had here in this updated image. So for example, now my head is moved to this direction, and ideally what our point tracking technique would do is find my nose at this location here. And what we do then is, again, we have an image patch or a feature patch around our current handle point. So this PI gets updated throughout our iterations. And again, we have an omega with this expression. And what this actually means is, before we had a 5x5 feature patch, and this time it's 11x11. So the R2 here is 12. So we have an 11x11 feature patch around our current PI. And you can see this is in the dimensionality way bigger than this. And out of all those individual pixels here, so our feature maps are way bigger, which indicate those 3 points. We compare the closest neighbor. So which of those feature vectors in here are closest to the feature vector of our initial handle point, which was the Fi. So basically, now let's say we are here, we have a small window around my nose, and we try to find the point, which would be the tip of my nose, that is the closest to our initial point, which was here, this feature vector basically. And that's what we're iteratively are doing. So first we slightly move our handle points towards our target points, and then we relocate our handle points so that we can use them in the next iteration, so that they're accurate again in our motion supervision technique, because here the omega 1 patches rely on an accurate position of our handle points that are getting updated in the point tracking technique. So basically what we're then doing, first motion supervision, point tracking, and it's like a loop. Do it again and do it again. And after the authors say like it takes 30 to 200 iterations in their experiments to basically reach all their target points from their handle points. And yeah, that's the whole, I would say, the whole magic behind the paper. And now let's just implement it ourselves.
Okay.
Hey, Ted. Oh, you go ahead.
So, so I don't know if I said everything quite right, the first time, but so the gist is that we're working in this feature map space. So again, this is where you take the W, you pass it through a single layer, you do a matrix multiply, and then basically you've got this feature map that's informing the other part of StyleGAN, which we're not modifying, how to tweak the picture as it sort of passes through all of these layers. Okay, so the first step is, if I just want the feature map to move a teeny bit in the direction that we want it to go, okay, and I figure out what tweak to the random number, gives me the closest to that. Then I do a forward pass with that random number, generate the whole image, and then I just look in this region around where the original handle point was, so the tip of the nose, and I say sort of which pixel in the feature map looks the closest to what used to be the tip of the nose. And it could be the same one. It could have moved one, or, depending on, sometimes it might move a little farther. That's why they've got this 11 pixels in every direction. So what they're counting on is that you're taking very small steps. So just like, Sally, you mentioned diffusion before. Diffusion wouldn't work if you took really large steps. You have to take somewhat small steps. So in this process, if you take small steps, like if you take a really huge step, then the shape of my nose changes from when you're looking at it straight on from one side. But when you take really small steps, even though it is changing the angle, it's changing it small enough that at the local level, it doesn't really look that different. And so both of those steps are taking advantage of the fact that with a small step doesn't change that much. And I thought he did a pretty good job of explaining why, if you're saying, here's a 1024 by 1024 picture, and I'm going to start with the pixel 500, 500, and I want it to move 100 this direction, you can't keep saying, I want 500, 500 to move in that direction, because at some point, once I've moved enough, 500, 500 is at the cheek. No, now you want 600, 500 to keep moving in that direction. And now you want 700, 500 to keep moving in that direction. And so that's why you need to keep changing the red point, the handle point needs to keep moving as you successfully shift the picture a little bit. The blue target point never moves. And so then the whole thing stops when red and blue get close, all the red and blue get close enough, or else max iterations have been exhausted.
Ted, your blue references the ultimate end goal of where you want to be?
Yeah, so in the original, what you'll see is the handle points are red, the points where you said this is what I want to move, and the blue is where I want it to move to.
Got it. Thank you.
So red at the nose and at the chin, and then the blue says move the nose up, move the chin down.
Right. Okay.
Hey, Ted, can I just ask a tactical question? And I missed a little bit there. My signal dropped for a minute. So you may have already answered it. So I apologize if that's the case. But he uses the term feature maps, both to describe the target and that reverse, whatever it is, fully connected connection that creates, I think it was W. And then he also uses feature map to describe what is essentially being used for the semi-supervision, which is the object features which need to move. Are those, my head's not 100% around this, but if you use the exact same layer, and I think you used, by example, just randomly picking layer 6, doesn't that present a data leakage problem?
I think we may have just, oh, there he is. He's back. Ted, you're muted.
Sally, you jinxed me. My internet dropped out.
One me, you 0, and then now me 0. All right. Did my question come through? Because my connection's dying.
Yeah. Yeah. So I don't know if I have a good. Am I sharing my screen again?
Yes.
I don't know if I have a good diagram to explain it. If I remember right, you start with uniform random number Z, you pass it through this deep network to get random vectors W. They're no longer uniform, but they're still random. You multiply that by a matrix, which allows it to basically just like pull out a subset or whatever of W, not use all of it. And then this blue box that's adaptive in, what I remember, it's not really shown here, but that this basically gets turned into a square instead of a vector. And then this square sort of supervises the transformation of your temporary image. So you have a temporary image and it keeps passing down here, and it gets tweaked, and then eventually it also gets upsampled. That's the little gray box here. But so there's these two steps. I don't remember the exact details, but these two tweak steps, if I remember right, this is a vector, like 128 floats, but then this turns into like, well, let's use the step down here. This turns into like, the picture right now is only 8 by 8. It's very coarse. This turns into an 8 by 8 square to match the image, and that's supervising the updates to each of the pixels in the 8 by 8. And then eventually sampled, and then they're doing this at like, say, 256 by 256. So we do have a link to the paper, and I might be.
So the question essentially is, you're basically using the feature map for both creating W and for supervising. Doesn't that create a data leakage problem potentially? Or is that maybe the whole intent of this thing, is that by having that data leakage, which is actually capturing the semantic data of the image, we win and it's easy to train?
Yeah, well, so it worked. So like I can cheat and say, yeah, David, it's not a problem. but I think why it's not a problem is because our feature map is not the actual image, right? This is in feature map space. This is not in pixel space. Okay. Hold on.
Dave, Sally, are you asking the question about when they were originally training StyleGAN?
So actually, I think I misspoke. So let me just quickly pull up the StyleGAN paper. But actually, when he says feature map, I think actually what he's referring to is the temporary image at that stage of the thing. So the 256 by 256 image that has not yet been fully finalized.
But then
So,
still, like if you're operating at that same layer, right? If both
yeah.
The training of W, which is essentially an input to the whole system, is if W is trained off of, again, this like layer 6, and then layer 6 is then also used to supervise it, that's causing me, I can't quite put my finger on it, but it's causing me.
No, so the first part, the motion supervision is clean because it's only using it once, okay? It's simply saying, what's the best direction to tweak my random number generator?
Meaning that it's not doing ongoing back prop and differentiating it when it's also adjusting. Got it. Okay, that right. Makes more sense.
So it just does that to say, how do I tweak the random numbers to get the nose to move in the correct direction? Then it's basically just simply asking, has the tip of the nose, has my handle point moved? When I successfully did everything in that direction, has my handle point moved? And if it has, then for my next iteration, I want that to be my starting point. I still want the handle point to be the tip of the nose, not just hard-coded at coordinate x500, y500.
I think I got it. I think it's handled by the fact that one of those is not operated on when the other is not being operated on, but it's all dependent then upon whatever layer 6 is being rad. And if layer 6 is rad, then this thing works.
Yeah. So I'm pretty sure, scratch what I said earlier about taking the random numbers and turning them into a square. That may or may not happen. But when he says feature map, he's really talking about you start with a 4x4 and you could very loosely call it an image. Okay, you have a 4x4 image, and in this case, StyleGAN 2, I believe it's always 2 steps. So you have a 4x4 and then a new 4x4, and then it goes to an 8x8, a new 8x8, and then a 16x16, a new 16x16 until you get to your final resolution. Okay. Technically, in ML, in computer vision, we never call those images because they don't have red, blue, and green channels. We always call them feature maps. And so that's what I think he's just saying. It's the intermediate image, as it were, but it's not red, blue, green image. It's got, first of all, it's got more than 3 channels. Okay. It's got other channels, but generally speaking, the understanding is that the physical location in the feature map does correspond to the physical location in the final image. Does that make sense? So when I start out with 4x4, the information contained in the upper right corner is going to correspond to the various pixels in the upper right quarter of the eventual 1024 by 1024 image.
Hey, Ted.
Yeah.
I found the description of, or a description of the add-in block. It says that the style vector is then transferred and incorporated into each block of the generated model after the convolutional layers via an operation called adaptive instance normalization, or ADA-in. The ADA-in layers involve first standardizing the output of the feature maps to a standard Gaussian and then adding the style vector as a bias term. So that's what that little block is doing.
Sorry, I had to mute. So how does the adaptive in apply to a square picture from a linear vector?
Yeah, I don't see it here describing that.
Okay.
I guess it doesn't, the shape doesn't matter so much as long as the dimensionality matches. And I would assume that the affine transformation, creates a mapping that's a large enough output to bias each of the features.
Yeah, they could do that. They could just output it and reshape it to be square, but I just wasn't sure. But the bottom line is that I think when they say feature map, they're talking about this temporary image, which feature map is the more technically correct name. But so it starts out like you can see it's only 4x4 in terms of 16 pixels, if you will, but each pixel has 512 chains. So there's quite a bit of information packed in. Since it's a 4x4, it's actually 16 total pixels. But they are they do geographically, so to speak, correspond to what will eventually become all the fine detail pixels in that particular region of it. And so, for example, if it's a centered headshot, then like the middle top pixels will correspond with hair. And so like they will definitely encode information as to like hair color at, at that very coarse level, and then have other things. So if there's a background, they'll encode information about the background that's behind the head and things like that. And so then if one of these is in the middle of the face, it'll definitely encode information about like skin tone and, things like that. And eventually, as you get higher and higher resolution in the X and the Y direction, and you have like a 256 by 256, then there's less and less information being encoded because you're now describing a much smaller region. There's less you really need to know. This area that's in the middle of the cheek doesn't need to know anything about glasses or earrings or hair color. It just needs to encode a small amount of information about skin tone and lighting and, is it shiny? Are you sweaty? Is it whatever, those kinds of things. So I don't know, did that video make sense? Do you guys feel like you get it? All right, cool. So here's,
sorry. The part that I'm still missing a little bit is this as I'm regenerating the GAN and I have this loss function. Is this, at one point you kind of described it as almost, Sally said, kind of a brute force search. But then there's I would think there'd be like a gradient, a directed path. And so it sounds like that's the one part that, for me at least, is still missing how that's done.
So and I apologize if I sort of misspoke at the beginning. But so I believe they're using gradients to update the random number vector, but for the point tracking, they're just doing a brute force search.
Okay, that fits. That makes sense then.
All right. So if we watch this video, I think they're going to do multiple changes to this original dog picture. Okay, it's not just one. But let me
Hey,
just
Ted, before you start the video, just one quick question. Did
Yeah.
they talk about the mask details, like how they determine the mask or how big it is? Like in one case, in one of the examples, they had the dog who was standing sit down because they pushed its tail all the way down. So the dog who was standing with 4 legs visible, the whole picture changed, right?
Yeah.
The whole dog is now down. So that's different than turning the face where it's only a small portion of the picture that changed. So I was wondering if they had some intuition or discussion on the mask.
Well, let me just show a couple examples and then maybe it'll be more intuitive, but if not, I'm happy to try to answer that. Okay, so they drew two target points, the red dots, and they said the top one they want to go up, the bottom one they want to go down, and then I think they also drew 2 points for the front legs, and they set the targets to be identical, meaning don't move the legs, but just open up the mouth. Now they just added 2 points and they said, move the ears. So they changed the ears. Okay. And they're showing this pretty quick where like they said it was like 30 to 200 iterations. They showed you all those iterations in the span of like a half a second, a quarter second. So there, again, they had 2 target points and they just moved the ears and the rest of the dog. They have not done any masking, so they haven't forced the rest of it, but in general, it's trying to just move those and not the rest.
Hey, Ted, can you back that up just a sec? Or
Yeah.
you could just do it with this one. It looks like the background is changing too. Has anybody else seen that?
It is going to change a little bit, but what they're hoping is that it will change negligibly.
Well, there's no mask right now, right?
There's no mask. And remember, what they're doing is they're picking a new random number vector to generate the image from scratch. There is no inversion in here.
Okay.
So you can't be guaranteed that when you tweak it a little bit in order to, in this case, move, you know, the back end of the dog to sit down, there's no guaranteeing that not only could the background change a little, but it could change catastrophically. This dog could change into a wolf, hypothetically, when you change the random number vector, because it's not, you know what I mean? There is no slider for just position of back of dog that's guaranteed to do that and nothing else.
Okay.
So,
it's just
in some sense, that's
violating
what's actually impressive about it, is that there isn't a known way to do that, and so they're still successfully doing that.
Okay.
So Ted, one just thought occurred to me here is that typically when we think of a loss function and gradient descent, we think of following the gradient into the weights. In this case, it sounds like they must be using the gradients back into the latent.
Yeah.
To decide how to change the latent. So
you can download a already trained GAN, and you could do this. And that's what we're going to do next week. We're going to download a pre-trained GAN that already knows how to make faces or animals or makes landscapes or does whatever. And we don't need to do anything with that. And we will freeze the weights and we will never change them. The only thing we'll do is we'll pick a random number generator until we get an image that we like. Say, oh, that's a good starting point. But let me change this one thing. Let me take this dog and instead of standing, I want it to be sitting. So I'm going to pick a handle point near the back end of the dog, and a destination point that's near the ground. And what we hope is that the dog will sit and that the dog won't turn into a wolf, that the dog won't get distorted. Now, what's really unlikely to happen is the dog's not going to become a 6-legged dog, because the GAN knows about the real world and it won't it won't ever generate a 6-legged dog.
Right.
Okay, so now they did a mask. So hopefully your background and your tail are never gonna move in this one, because you said I only want that part of it to move. And then, let me see if I can back up a little bit. They said, move the nose. Oh, you can't see me pointing at my screen. They said, move the nose, this red dot, quite a bit towards this blue dot. So hopefully only the head turns and that the tail and everything else stays the same. And that's what they do. And it's very sped up here. This doesn't necessarily run quite this fast. So that red car, you saw the car style actually changed a little bit. They just wanted to rotate it, but I think it changed.
Also, the background changed fairly dramatically if you look at the windows.
Oh yeah, you can see the building keeps changing, right?
Yeah.
But the kind of it's kind of similar in that it's like white and brick. But so yeah.
But again, there's no mask in this one, so it's okay to change the background.
Yeah, and I don't know there's a guarantee that if you mask that it still wouldn't change the building some.
Yeah, it would have to, because as you rotate that, various other parts of the building that aren't in picture are exposed.
Yeah, but even like the parts of it that really didn't have to change, they still might. They're not supposed to. There was one picture where they had like a lion, and I think they had the head move a lot or whatever. And I saw that like the not masked part of the back of the body, it actually moved a little bit because they wanted the head to move so far that you couldn't move the head without actually like moving some of the shoulders or whatever with it. Does that make sense? So,
Sure,
I saw there was at least one picture where I thought it did what I would have done as a human if you told me to make that change. I would have said, okay, but to be realistic, I have to actually change a little bit of what's outside the mask region. Otherwise, I'm going to get a really distorted, weird looking line.
You know, what's interesting about this approach, Ted, is that it sounds like the features that we're wanting to transform are the features around the red dot, right? So the headlight in this. So when you rotate it, the headlight might move, but the style of the car, that isn't in that little 3x3 matrix that they used, or window. So some of those things could change.
Yeah.
As a human, you wouldn't think of changing.
And there's going to be some subjectivity, okay? So like there was one where they had a woman wearing white pants and they were like 3/4 length, and they picked spots on both legs and they moved it up and it became like knee length culottes or something like that, right?
Mm.
Like hypothetically, you could have made the woman taller and she could have had really long shins. You know what I'm saying? So ultimately the model does have to kind of guess what you mean. And so it doesn't always do it right, but it seems like it generally, because the GAN is already, again, got world knowledge, it seems to generally do relatively smart things.
Well, I guess once you select a point, right, you have logged in your latent that you want to modify. And if that happens to be I missed exact example that you were picking up, was it where a woman wearing a sweater becomes a long gown kind of thing or something like that? When they pull, I don't know what example you had, but then if that is the case, then they know what exactly to modify, and that the rest of the latents will keep the style.
Yeah, it's possible, but I'm saying if you have a picture of a woman with 3/4 length pants and you pick only 2 handle points, which are at the bottom of the pants, and you move them up, theoretically, a valid change would be to change the woman's legs or whatever. But again, it's looking to make the minimal change, and it's the one that seems intuitive to me. But you're counting on like a lot of baked-in knowledge. I think this is the one where they had the lion's head move quite a bit to our right, and I think it moved the leg a little bit because like you can't move the head that far and still have the leg planted all the way over there. let me just play this for a sec to see if this is the one. Oh, it did move the body, but they didn't mask it, so that's not exactly right. And I think the line changed a little bit.
No,
Let me see.
the way they moved the body made sense, though.
Yeah. Again, the GAN has a lot of real knowledge. So this is the one I think where they keep changing her clothes. So they only moved one sleeve, but this thing was smart enough to know your sleeve should match.
I know this one is playing, but it was not really smart enough that the sleeve should patch. But because now your hand should be more exposed, so it had more hand exposed in that one. That was, yeah.
Oh, that was cool. It lengthened this, but this has a pattern, so it had to continue the pattern, right? So,
It's
so
quite impressive.
That's the gist of it. I don't even understand. This is like some single-celled organism in a microscope or something. Like I don't even know. Like as a human, I didn't know what you're supposed to do when you move this handle point.
I just thought it was a UFO in the sky.
Are you just rotating it, or are you also flipping it? Or are you twisting it? Like
I
don't even
wonder
know
if
what
they're
this is a picture of.
showing. Well, they moved it twice, and that forced a twist, if you will, into the object. I wonder if that's what they were trying to demonstrate.
Yeah, and I don't know if that was undesired or desired.
And that's the training data set, right? So it knows the world that it is.
Yeah, I don't even know what GAN knows how to make single-celled organisms. But so in that case, you saw it sort of shrank the outside cell wall, but it didn't shrink the innards proportionately. And maybe that's wrong, I don't know. Like it wasn't given explicit instructions. Somewhere in the paper, if not in here, where's the paper? I guess I haven't clicked on it.
No, it was there, Ted, I think.
Oh, here it is.
Yeah.
You can see somewhere in here, I haven't read the paper fully cover to cover yet, but they have some examples where you can see there's like 30, 50 points. Yeah, see this?
Oh, yeah.
So I'm not exactly sure what this is, but it's like they wanted to make the face less round and more skinny oval shaped. So they have a whole lot of anchors and movement or whatever. So this is like a lot of supervision. So if you want to like tell it, exactly what to do. Or no, this one, maybe it's rotating the head side. But again, the point is like, theoretically it runs slower, but there's nothing stopping you from having a lot of handle points in order to tell it like, don't move this hand and don't change this length of the hair, or you know what I mean? Like if it moves something you didn't want it to move, you can just add new anchor points to say, don't move it.
That is pretty impressive, though. I mean, that they would, put that in there so that somebody who was an artist or something like that could come back and make it more realistic.
Yeah. I saw something, where it was like making a photograph of somebody who's not necessarily super skinny and like making them look skinnier. And I was a little bit like impressed with the technique and a little bit like afraid of just sort of like societal norms being reinforced by, everybody has to be skinny in pictures,
I think those filters already exist in.
Yeah.
Yeah, I've seen those filters, people using it all the time. But
Yeah.
yes, this may be yet another way to do it.
So I like this
Yeah,
one
Tim.
where they have two eyes, and on one of them they keep them still. On the other one they say bring them together. So they got the cat to basically wink. Okay, because normally if you bring them together, it would close both eyes together. And so having these extra anchor points forced it to keep the other eye open. So
Oh,
just kind of
that'll be in a commercial, cat food commercial sooner or later.
yeah. So
So
hopefully
I was just reading the caption for that, and the thing that mentioned was this W plus, the middle one, is actually out of distribution manipulation. So they never saw any of this picture, of course, as you can imagine, and they could generate, or style, if you may. In this case, it's the style. Of course, they may not have seen all the images, but that's just super amazing.
I'm gonna have to read about this. Yeah, I'm not quite sure what they're saying there.
So closing only one eye of the cat is an out of distribution image. If you made, they did not have any cat image, possibly even animal image, with one eye
Right.
open and one closed. And they,
But what's W plus? That's what I don't know.
that's the middle one where only one is open and the other is closed. And W
Right,
is
but
when
But
both
what
is
actually
open
is
or closed.
W plus space? I'd have to read the paper, I think.
Maybe cats can't wink.
Yeah.
They can blink,
saw
obviously.
in the code, one of the notebooks, it talks about having trainable and untrainable latent. So I'm guessing that might be that they're actually kind of augmenting the latent, and that's how they get outside of the distribution.
And when you say untrainable in the original style or the default style GAN.
That's what I'm guessing. I need to read
Or
through. I haven't read.
no, you may be right. It may be even training for this. Like somewhere you need to begin with, right? You need those images. Like I'm one thing that I was thinking was, how would have they trained it to, like the supervision training? Is it through the videos? Like in video you have different frames and then you pass those along and say, well, this is how you turn the head, and these are, and when I move this point to there, then this is exactly what is happening. And they would never have a latent for the W plus, whatever is there in the middle, whatever you may do.
Yeah.
So you can never train for that latent.
Yeah, and remember, the GAN is frozen this whole time. The GAN never gets modified.
Right. So when they're saying training here, I think it's the portion of the latent that they're modifying to achieve this, the visual output that you want. And it seems like to me, one of the issues is that we're, as the human, we're dealing in these probably not entangled abstract features. And that's what we want to change. We want to say, lion, turn his head a little to the left. And we're having a problem trying to map that onto this visual cue of exactly what is it that we want to do. So by kind of using this point in the image and motion of that, we're trying to infer the latent that we actually want to modify, and it doesn't always work. It doesn't map well.
Yeah, I mean, there's sort of two separate issues. One is from just a couple red and blue dots, does anybody, computer or human, know exactly what you mean?
Yeah.
Like
if
you do one point here on my lower lip and then you say move it down, does that mean tilt my head down, or does that mean open my mouth? Right? It's ambiguous just from that.
Or you move it down. Yes. Yeah.
So the poor GAN, I mean, has to deal with that level of ambiguity. But then the fundamental thing that they've solved is there is this thing called GAN inversion, and that's a whole separate beast where you can get an approximation to an image. But this is fine control, which GAN inversion absolutely cannot do. Okay.
So GAN inversion, does that mean, because with these, I can't just modify a picture that I have. I have to have a GAN generated picture and then I can modify it, right? So GAN inversion, is that allows me to take my photograph and find the right latent that comes close to generating that?
That's right. So if you have a GAN that knows how to do cats, maybe other animals too, but it knows how to do cats. If you do a picture of your cat, it'll come up with something kind of close.
Okay, so that's closer to what Selly was talking about earlier when he was talking about kind of this inverse diffusion, right? You're going from an in distribution image back down to a Gaussian distribution latent.
Yeah, and I think
it's kind of what the inverse GAN is doing.
I think that the diffusion problem is much fancier and harder, right? Because they're sort of saying, how do you denoise something? And in the early stages, when it's just really noisy, it's very hard to denoise, right? Once it just looks like a slightly staticky picture of a house, then like fine, take out the pixels and it'll just be a nice clean picture of a house, right? But in the early stages, when it's highly noisy, how you denoise that is really, really hard. How you take a picture of a cat and just shift the head a little bit to the left, theoretically, that's not nearly as hard. I mean, it's still hard, but it's not nearly the same, right?
Yeah.
And so they have a clever way of saying, let's tweak our random numbers just a tiny bit. And the trick is figuring out which is the right direction to tweak them.
Right.
And we'll take small steps. And if we just did that and we did nothing else, you would actually find you can only make small movements, because at some point, what used to be your anchor point, your nose, is now somewhere else. And so now what you'd be instructing it to do is to move the cheek. So that's where they came up and said, we actually need two steps. We need the one thing that does the moving, and then we need something else that tells us, has our starting anchor point shifted? And if so, then we need to give it a brand new starting point.
I have a question, although it may be a novice question. Do they discuss in the paper sort of what kind of distribution or variety that you need, or I guess uniformity you need in the test data to make this work? In other words, here is one cat, right? And the idea of this method, as I understand it, is that you can train it to be able to manipulate any cat based on some subset of data. But that seems like there needs to be a criteria for how similar or how consistent, I guess, your training data set needs to be. In other words, if you threw a horse in there, it seems like it would mess it up. But you still want some variation. Do they talk? Is there a mathematical way that they discuss about parameterizing a good training data set for an application like this?
So in this case, the problem as defined by the authors, is self-constraining. You can only modify an image that the GAN created in the first place. So this GAN inversion conversation aside, I can just simply click the button, say, generate me an image, generate me another one, another one, another one. Oh, I like that one. I'm going to modify it and change the eyes on that cat. So it's already an in-distribution cat because it generated it. So yes, so that problem that you're talking about just doesn't come up because you can't, quote unquote, give it a horse. You're always starting with an image that it generated.
Right. So, Human, one other way to think about this perhaps is that this is based on a pre-trained StyleGAN 2 model. So, the amount of data that went into training that StyleGAN 2 model is, well, it's available in their paper, but I think it was quite a bit. there was a large training set. So when they were training that style GAN2 model, that's when they would have seen lots of cats and lots of horses, etc., and cars and trucks.
So like I don't know animals really well, but let's just say you have some animal that looks a lot like a rabbit but has small ears. So maybe a guinea pig or something like that, right? And if you had a style GAN that was trained on hundreds of different kinds of animals, so it knows lots of animals, including guinea pigs and bunnies. If you told it to like make the ears longer and longer and longer, I don't know, at some point it might just start shifting,
Turning
it
it
into a bunny instead of a guinea pig.
Yeah.
I don't know enough about the animals. Maybe you can't even tell the difference at some point. Like, what is a guinea pig with long ears? It's a bunny, you know. But nevertheless, like I could see that at some point you might have certain things that it just does because of kind of what you're talking about. It was only trained on something. It was never trained on long-eared guinea pigs. It was never trained on short-eared bunnies, and so it has to choose something. What's like, again, since it's not allowed to get feedback from you,
Yeah.
what's more reasonable? What's more unreasonable? Making this a bunny, or saying that it's a extremely long-eared guinea pig, even though I've never seen one. So like I think we couldn't necessarily criticize it for switching it to a bunny, because maybe in its world it just thinks that that's more realistic.
Great, thank
Hey,
you.
Ted,
So the other, just wanted to add one point. So like, in
Sure.
diffusion, if you give the same prompt every single time, you will get different images. I mean, it will follow the clue. It's a class, the classes will be same if you have name of a dog or whatever. It will follow that clue and try to generate the same image. However, the latent that it operates on, the clip guided latent, because diffusion model is stochastic, highly stochastic process, so follows that. So it can lead to following the guidance, but different images. In this case, as Ted was explaining, the latents are highly specific. That whatever be the size of those are highly specific. If you try to change it in certain direction and you use it every single time, it's going to generate almost the same image. There is some noise that's coming on the right hand side, as we saw that in the style GAN, but that is not as prominent as would be in the diffusion or remove the noise of diffusion process. So it's the same thing to try to do in diffusion is going to be really hard.
Yeah, I'm not sure of an immediate analog to this that you could do in diffusion paper, but this is really clever, and I'm just, it's cool looking. I don't know if it's just cool looking because it's pretty pictures. Like, I'm a sucker for papers with pretty pictures,
Well, thanks, Ted. That's a really good job on that. I'm going to stop the recording here real quick.
Yeah, sounds good.
Yeah, I was going to say,